So let's talk about limits, quote, at infinity. Really, you never can get to infinity. So at is the wrong kind of word to use, but we use it anyway because what we're generally writing is something like we write the limit x arrow infinity, and I'll just throw in a random function here, e to the negative x. Right? And then we have equals, or we're asked, find out what this equals if it has a limit, or explain why it doesn't, something like that. Or say it has no limit, or if it does have a limit, give the value. So x arrow infinity, technically we should be saying the limit as x approaches infinity. Just like every time we see an arrow, we should say approaches, but usually we say at. Anyway, this is a really good example to start with, e to the negative x, because there is an answer. I think you've known since either algebra or pre-calculus that the exponential function, right, that's exponential decay. It's got a negative exponent. And I think you know that it gets closer and closer to zero, but never gets there, right? If you think about it, this is really 1 over e to the positive x, right? That's another way to write it. And we know e to the positive x, right, as x grows larger, that gets bigger and bigger and bigger, but it doesn't matter. There's a 1 on top. So 1 divided by anything as huge as you want still isn't going to be 0. But of course, since you get larger and larger and larger, your answer gets smaller and smaller and smaller. So you say the answer is 0 equals 0, which really in this case means as x goes up towards infinity, you can get as close as you want to 0. That's all the technical stuff at the beginning of the section that talks about epsilons and all that. You don't really need to follow all that, except if you look at it, you'll see that idea of as close as you want, right? You want to be a billionth away? Fine, I can figure out the x that'll make sure that e to the negative x is less than a billionth. You want to be a trillionth away from 0? Fine, I can find the x that'll make you less than 1/10 of the way to 0. 0 is what you're getting towards, and you're getting towards it as close as anybody wants. You just never get there, but you get as close as you want. So we treat as close as you want as equals 0. Technically, I think we should probably have an arrow, right? As x goes towards infinity, the limit goes towards 0, but all limits are about going towards and never equaling. So we have the convention of equals for getting as close as we want. And of course, just because you have a limit on one infinity does not mean you have the limit on the other, right? What do you mean other infinity? The negative one. There's 2 infinities, right? There's the one on the left and the one on the right of plain old e to the negative x, right? And think about that one. We could just look here, or we could, right? It's just going up without bound. Or we could think about, right, e to the negative x. Well, as we're going towards negative infinity, negative x is positive. And as x grows more and more negative, the negative of a negative grows more and more positive. So we keep putting e to larger and larger powers, which explodes upwards and gets large. So I guess this would be a case where we could write down positive infinity as the limit, but this is something we generally don't do. Generally, instead of stating the infinity you go towards, we just say the limit does not exist. Vertical asymptotes, right? We don't say the limit is infinity, right? We say does not exist. And essentially, this will take care of anything you do. You can graph it on your calculator, take a look, and essentially you're always going to be able to tell. Sometimes you'll need to zoom out because if you've got a bunch of polynomials, things get confusing. If you've got, I don't know, sine functions involved, trig functions involved that go up and down, things might get weird also. So the crude way, graph it and zoom out and see what happens on the left side and the right side. So that's the, let's just say the backup method. There are easier and quicker methods for some kinds of functions, right? But graph is your last resort, and sometimes it'll be your first resort if you look at the algebra and go, huh? Let me show you an example where the algebra really is what you wanna do. So this is x cubed plus 3x squared plus 17x. And I'm going to be a little silly here, plus a million, right? There's a point to the million, I promise. And let's just go ahead and put, let's put x cubed again. And I'll just make it a little simpler, plus 18x. Right, and let's take the limit as x goes to positive infinity. Sorry, that came out as a 2. I said x cubed. So what's going to happen here? Right, the issue is there's no factoring here. I mean, you could factor the x and the x squared plus 18, but there's no way to factor the thing on the top. So it's not like those examples where you can factor and you've got a vertical asymptote and a hollow dot. Those are the sort of gentle polynomials that you see in continuity questions. This is just brutal, nasty algebra. And look at this. This million is so big. So think about that. Oh my gosh, that million is so big. I bet you that the limit has to be really big, right? Because it's got a big number. The values here, when you plug in x's, are going to be big. But remember, we're allowing x to march off to infinity. X itself could be a million. When x itself is a million, this term here is 17 million. This term here is 3, what's 3 times 10 to the 12th power? It's got 12 zeros in it because a million times a million has 12 zeros. I guess that's million, billion, trillion. That's going to be 3 trillion here, right? Way longer. And this one, oh my goodness, it's got 6, 12, 18 zeros at the end. I happen to know that is a quintillion, right? I love numbers, so I memorized them when I was a little kid. The extra things beyond millions and trillions. Millions and billions and trillions, which I'd heard about. What's after that? And my grandpa let me loose on his old-fashioned dictionary, and there they were. So a million doesn't mean anything as a constant when you're allowed to let x be as big as you want, right? When you're looking at 1 quintillion, right? A million is just, it's like a trillionth of the value here. It's so tiny. And that's the key. Look what we just learned. This million is equal to this, in the same order as this because it's millions. But so what about the 18 million you have? Over here is 3 trillion. So compared to 3 trillion, 18 million just disappears. It's just minor error. And even the 3 trillion here, this term is almost a million times larger. It just becomes error. So, right, because when you write the 3 trillion, I mean, the 1 trillion, you'll have 1, 0, 0, 0, 0, 0. There's a 3 finally out here. And then there's a 0, 0, 0, 0. I think this is where the 1 and the 7 show up. And then there's still 6 more zeros. This is ridiculously small. The numbers created by the other terms, the 3 and the 17, sorry, I should have been 18, are just completely minuscule compared to the dominating beginning. So they become error. And here's the deal. It's because the polynomial degree is smaller than 3. So that's really all you have to do with polynomials. Look at the dominant polynomial degree. Don't forget that x is really x to the first. And technically, you could think of constants as x to the 0. The largest polynomial, the degree of the polynomial, is the only term you need to look at, right? 18x is error compared to x cubed. Same reasoning as here, right? It's 2 powers less. Pick a big number, and the 18 times that big number is going to be very, very small compared to that big number to the 3rd power. So this is just error. And then what you can do now is you can reduce and go, oh, it's 1, and then there's a little bit of error here, plus or minus some error. And that's okay. Remember, we're allowed to have a little bit of error just so long the error gets as small as we want it to. That's the technical definition, right? And remember, we can make x as large as we want. So it's not going to be too hard to make those errors shrink smaller and smaller in comparison to the big number cubed. So we say the limit equals 1 because we can actually get as close to 1 as we want to. And this works for anything that's polynomial, right? And it just becomes a matter of, right? So I'm just going to write, I don't know, I'll write 2x plus 2x squared plus, and I'm just going to scribble it out because we don't care if it's all polynomial terms. And what about, you know, whoops, I don't know what that was. What about if the bottom of the fraction is, you know, 20x? I'll write the number plus 1. Right, well, the plus 1 is error. This is all limit as x goes to infinity, so we'll just pretend that's right here, right? We just scribble out the non-dominant terms, the non-highest degree terms, and then we cancel what we can, right? The 20x and the x squared, well, that's going to cancel x with x squared, and we get 2 over 20. That's 1/10, and then x. But wait a second, as x goes to infinity, well, x will go to infinity. So this has the answer of does not exist. Although technically, you know, on a graph and looking at the algebra, we know it goes to positive infinity as a limit. But we really didn't even need to do this to see that. And we didn't even really need to scribble all these things out. I mean, we just ignore them and we just go, look, x squared is larger in polynomial degree than x. So remember how the small things, the lower polynomial degrees, don't matter. They get tiny compared to the higher polynomial degrees. Well, if the bottom of your fraction gets tiny with respect to the top, then you've got a tiny thing on the bottom and a large thing on the top, and that goes off towards infinity. And the beautiful thing about that is the reverse also applies, right? So if this is x, and now I'm just going to be totally abstract, x to the power n, and nonsense here, and then, right, that's all error. And then what about if this is x to the, I'll do the example of n plus 1, right? What if your bigger polynomial degree is on the bottom? Well, again, you're just going to consider everything else error, And when you look at these two terms, oh, the smaller term is on top, the bigger term is on the bottom, and right, things are going to cancel out, and then, you'll just have 1 over x. And of course, if this was higher, like 2 degrees higher, you'd have 1 over x squared. 1 over any degree of x. Oh, as x or x squared grow larger and larger and larger, and you have 1 on top, that's just like our e to the negative x. The limit is 0 when the polynomial on the bottom is big. So you've got immediate rules. When you have polynomial fractions, if the top polynomial is bigger, then does not exist. Limit does not exist. If the bottom polynomial is bigger, has bigger degree, then the answer is 0. And if they're equal in degree, then you simply look at the ratio of the highest terms and do the canceling, right? If this was a 2x cubed and that was a 5x cubed, then of course your answer would be 2/5 instead, right? Everything else becomes small errors. So for polynomials, things will work out nicely. For things involving exponentials, sines, etc., it's a little bit more subtle. And I'll just give you one example. You know what? I'll stick it in the corner here. I won't talk about it too much. Look, sine of x, it's not predictable. Cosine of x, it's not predictable. It varies from 0. It can go as high as +1. It can go as low as -1. So if you've ever got a trig function on the top, on the bottom of your fraction, forget it. You're not going to be able to predict it because sometimes you're going to be dividing by 0 when sine or cosine hit 0. That's never doable. But sometimes you have a sine or a cosine on the top of your fraction. Again, tangents, we can't use tangents either on the top or the bottom because they go off to infinity and go off to 0 periodically. So they're completely unpredictable. But sine of x and cosine of x, they just vary in a very small range, -1 to 1. So in the long run, yeah, they might be oscillating between -1 and 1. They might be going back and forth and having all the values, but that's the top of the fraction. Basically, they're near the constant 0. They're near a constant, remember? So if you're right, constant is polynomial of degree 0. So if you've got some polynomial of real degree, n greater than 1, then it's going to shrink to nothing, right? This will act like a constant. The trig, sine or cosine will act like a constant. And then the bottom will be a higher degree than just a constant. Of course, the fun begins when you have what about x squared over x cubed, right? What if x squared is times? Well, same thing. Sine x times x squared, that acts like an x squared polynomial, but it's being, sometimes it's smaller than x squared because sometimes sine is smaller than 1, but it acts like an x squared polynomial. So x squared over x cubed, we would just cancel out and go 1 over x. Oh, the bottom is bigger. The answer is 0. The tough thing is when you have x squared and x squared, maybe you've got extra stuff here that you have to cross out, right? You want to be saying, oh, look, same degree, x squared and x squared, same degree. Yay, no problem. The answer is 1 because I'm supposed to cancel out the degree. But yeah, it's 1 for the polynomial part, but you still have sine of x or your cosine of x times the 1. So when you get out towards infinity and the polynomial stuff cancels, you're still oscillating. You're still going from -1 to +1 as the sine of x, as x changes values. So just watch out for sine of x and cosine of x when they're mixed with other polynomials. When they're unmixed, you treat them like a small constant, and that's easy to deal with.